order correlation function. I think it'll become clear that it would be nice to have stronger interactions, and I'm going to describe a theoretical idea for doing this, where one can get stronger interactions by driving the phonons, and this is an idea that's been discussed in different quantum platforms that use boson-mediated interactions. And then if there's time, I'd like to describe how we can use the same spin-motion coupling to sense very weak center mass motion. And this might give us an opportunity to sense very weak electric fields and maybe search for certain types of dark matter, such as axions and hidden photons. So let me just review how pending traps work, and we have experts in the room here. Looking for it. So our trap is a stack of cylinders. We put a few kilovolts on these end cylinders relative to the central cylinder. That gives us an axial confinement with this type of potential near the center of the trap. And so this omega z, the axial frequency is around 1.6 megahertz in our work. Now this potential is radially deconfining. The electric fields point radially outward. We get radial confinement by immersing the whole trap in a 4.5 Tesla magnetic field. The way that works is the radioelectric field with the magnetic field. There's an E cross B drift, which is the rotation of the ion crystal about the trap axis. As the ions are rotating through the magnetic field, they experience a V cross B induced Lorentz force, which points radially inward. So in my talk, omega little r is this rotation frequency, and the point to emphasize is a parameter of the trap. It's something we have to control. And we do that with rotating electric fields. That's what these azimuthally segmented electrodes are for. And we can precisely control the rotation frequency, and that enables us to get these images of the crystal in the rotating frame of the crystal. I should say that this rotation frequency for us is going to be a little bit higher than the single particle magnetron frequency. But you can think of the rotation frequency of a single particle in this trap. So these images are obtained with a photon counting imaging camera. To get an image like this takes about a second, so it's a little slow given our current camera. And so many of the measurements I'm going to show you later involve global fluorescence because it's much faster. We have a new camera. We should be able to speed this up by an order of magnitude. So we shine lasers in, a crystal forms. The type of crystal that forms is going to depend on the size of the crystal and its shape. And so this plot shows the different crystal shapes and the density we get as a function of this rotation frequency. For very low rotation frequencies, we get these single plane crystals. If we apply a torque and spin it up, we get a 3D crystal. And we've observed with up to 500,000 ions, we've observed body-centered cubic crystals. These are 3D periodic crystals. In the work I'm going to discuss in my talk today, we're going to focus on these single plane crystals. Now, the techniques I'm going to describe, which work with the single plane crystal, I think in most cases can be generalized to these large 3D crystals. So that might be an interesting future direction. So just a little picture of the experimental setup. This is the trap as we were assembling it. This has been under vacuum now for about 3 or 4 years. And it's a room temperature experiment. This is a fused silicon normal stainless steel vacuum hardware that's get inserted into the bore. This is the room temperature bore of an NMR style superconducting magnet. So our spin degree of freedom, we work with beryllium, and beryllium has a single valence electron, and our qubit or spin degree of freedom is this valence electron spin in the 4.5 Tesla magnetic field. So the spin up and spin down are split by 124 gigahertz. There's nuclear spin levels here too, which are decoupled from the electron spin, and I'm not drawing them there for simplicity. We optically pump the nuclear spin, and it really never leaves the nuclear spin state during a given experiment. So we use standard techniques, the laser cooling and a cycling transition. This is our means of detecting spin up as a bright state, spin down as a dark state. We can optically pump and prepare all the spins in the up state. And we can globally control the spins with microwaves, which are resonant with 124 gigahertz. And from a quantum simulation language, these microwaves give us a transverse magnetic field in the rotating frame of the qubit. So the motional degree of freedoms, if we have n ions, there are 3n normal modes. And for our single plane crystals, they break up into 3 different bands. There are high-frequency cyclotron modes, low-frequency E cross B modes, and we use spin-dependent forces to couple to these transverse drumhead modes, as we call them. And this shows the video of the modes. This is from a code we got from the Fourier group for, this is a 300-ion crystal. The highest frequency mode, transverse drumhead mode, is the center mass mode. As the wavelength gets shorter, the frequency goes down. These lowest frequency drumhead modes only live in the center of the crystal, and there are ions in neighboring spots oscillating back and forth. So I like to advertise that we've recently been able to implement ground state cooling of the drumhead modes. We employ a form of ground state cooling called EIT cooling, which was some of the early theory was discussed by Giovanni Marigi. So EIT cooling involves this normal lambda configuration of laser beams. For us, it's these two beams have to be phase coherent and separated by 124 gigahertz. And we implement this EIT cooling with these two laser beams coming from the side at a plus and minus 10 degree angle. One detail, so there are some challenges of implementing EIT with these rotating crystals. One nice feature I wanted to mention is in this large magnetic field, because the levels are split out, we really get an ideal 3-level configuration. And that can be a challenge with trapped ions with hyperfine qubits at low magnetic field. These laser beams have a large enough waist that they cover the entire crystal, so there are Doppler shifts which effectively modulate this detuning delta. We take care to align the EIT K vector so it's perpendicular to the crystal, so we're only going to try to EIT cool the drumhead modes. Let me show you some temperature measurements. This is on the center mass mode. We use, for the trapped ion community, an unconventional means of measuring temperature. We measure the mode temperatures with a spin-dependent force. Basically, you can think of the spin-dependent force maps motional degree of freedoms, thermal fluctuations into spin precession. I'll talk about this in more detail later, but this is the interaction due to the spin-dependent force. If there's some classical thermal fluctuation given by amplitude Z sub c, that's going to give rise, when you put it in this interaction, to a term which, when the motional frequency is equal to the spin-dependent force frequency, just gives rise to spin precession. And so this shows the measured spin precession. We call it bright fraction, because we do this in an experiment where at the end of the experiment we rotate down. If we have full coherence in our block vector, that's a dark state, that's 0 count. So as we get counts, that corresponds to a shorter block vector. And so we get with the spin echo technique, right on resonance, the spin precession that happens in the first arm is canceled by the second arm. We get a 0 there. We get this line shape, which we can fit without the laser cooling, at n bar about 5.6. With EIT cooling, the spin precession is much lower. We get a very different line shape. When we're close to the ground state, this different line shape is because when we're off resonance, there are induced spin-spin interactions, which also shortens our block vector. So anyways, by fitting to these curves, we can extract an n bar of about 0.2 to 0.3. This is a slightly different sequence where we get a similar n bar. Advertise that this EIT cooling is fast. So this shows the temperature of the center mass mode of a crystal of 190 ions as a function of the duration of the EIT cooling. After an initial transient, this fits to an exponential with a time constant of about 27 microseconds. And the curious thing is that this is actually faster than what one would calculate based on single particle theory. And so I can't say we really understand why, but this is a coupled many-body system. When we put these EIT-K vectors on there, the spins are interacting with each other while photons being scattered, and the cooling is actually faster than one we get with single particle theory. This modeling was done by Athreya Shanker, who's a really good student at Murray Hollins. So this shows the measured spin precession or spin dephasing as we sweep a spin-dependent force across the full bandwidth of the drumhead modes. This is with Doppler cooling only. We can resolve some of these higher frequency modes. In general, we don't resolve this bandwidth of modes. If we follow Doppler cooling with EIT cooling, we see significantly less spin dephasing. Because we don't resolve these modes, we can't do a quantitative measurement, but we can say that this is consistent with near ground state cooling of all the drumhead modes. So let me describe how we implement a spin-dependent force. We use an optical dipole force. We take two off-resonant laser beams, cross them at 20 degrees angle. It gives a 1D optical lattice. By putting these at different frequencies, it's a moving 1D optical lattice. And so the gradient of that gives rise to a spin-dependent force, which we can adjust the polarization and frequencies of these beams so the force and spin up is equal and opposite to the force and spin down. And the time dependence is just the beat frequency of those two laser beams. So this is the interaction we're setting up here. This is a slide I grabbed from an introductory talk where I'm just talking about a 2-ion crystal, but we're coupling the spin and motional degree of freedom of each ion. And then to motivate, we like to drive strong spin-dependent excitations. And so in our work, we tune this spin-dependent force frequency close to the center mass mode. So I think everyone here understands this geometric phase picture of how we calculate the energy-dependent phase factors that these different spin states pick up when we turn on the spin-dependent force. The anti-ferromagnetic states don't feel any force. They aren't excited, but the ferromagnetic states are excited and de-excited. And after a time given by 2 pi over this detuning, we realize an effective spin-spin interaction given by this expression. And one point to make here, a fairly obvious point, is if we're only coupling with one mode, it's easy for us to change the sign of this pairwise coupling. We can jump our spin-dependent force from being above the center mass mode to the same distance below the center mass mode. So in our work, we couple to the center mass mode of crystals of 100 to 200 ions, and we do that by detuning this delta a few kilohertz away from the center mass mode. This is small compared to the splittings of all the other modes. And the expression on the previous page generalizes. The point to make here is that this pairwise interaction is now weaker than it is with the 2-ion crystal by this factor of 1 over n. And this came up yesterday in some of the talks, that if you only interact with one mode, as the crystal gets bigger, the pairwise interactions get weaker. One can try to counteract that by interacting with multiple modes. In our work, we aren't doing that yet. So this is a infinite range interaction. Two spins have the same interaction strength, whether they're nearest neighbor or on opposite sides of the crystal. And we can more simply write this in terms of the composite spin of the system. It's just S sub z squared, so this is single axis twisting, which has been realized in various platforms in AMO. And this, I think everyone here knows, generates a spin cat state at long interaction times. And the experiments I'm going to show, we access quantum dynamics to about 10% of this cat state time. So we do experiments where we compare all the spins pointing along x. This has some spin noise, which is orthogonal to the average spin vector. We apply the Ising interaction. This is not an eigenstate of the Ising interaction. Some non-equilibrium dynamics occurs, and then we measure the spin state after some interaction time tau. We can measure it in a general direction by rotating that direction to lie along the z-axis, do our measurement in the z-basis, and we repeat the experiment many times, measure the average polarization and the variance. So I think everyone knows the spin squeezing picture. This is just a lead-in really to the out-of-time order correlation. The spin noise in the northern hemisphere gets pushed in one direction, the southern hemisphere in the opposite direction. This shows measurements of that spin noise as a function of the rotation we do about the x-axis before doing the measurement. We can see the anti-squeezing and squeezing. I should say this is a logarithmic plot here, and 0 corresponds to the spin noise before we apply the interaction. So as we increase the interaction time, more anti-squeezing, more squeezing. Two theory curves here. The dashed line is single axis twisting without any decoherence, and the solid line is the prediction of the spin noise which we should get if we include decoherence due to spontaneous emission. And then at longer interaction times, the squeezing disappears. So what's happening here, the squeezing disappears when the spin noise is starting to wrap around the Bloch sphere. And at that point, this is a non-Gaussian state. It's no longer well characterized by the second order moment. So one has to use other techniques to try to characterize that state. You can look at the full histogram of the spin noise measurements. We've done a little work with that, but I like to describe now how by measuring at-a-time order correlation function, one can benchmark these oversqueezed spin states.
John, this picture on the left, that's some representation of the data you measured, or?
It's meant to be, when this happens, the spin noise is wrapping around the Bloch sphere. I forget, this is 3 years old, I forget whether this particular histogram corresponds to this curve, but it would be roughly what's happening, yes. So if we looked at this, the histogram corresponding to this curve, when we would measure the spin noise in this direction, it would go from plus n over 2 to minus n over 2. So what is an out-of-time order correlation function? So this is the object. It's the expectation value of operators V and W. V and W are usually assumed to be unitary, and they commute at time t equals 0. But the funny thing about this expectation value is that these operators are evaluated at different times. So why this object is of interest is one can rewrite the real part of f as 1 minus the commutator of V and W. At time t equals 0, then the real part of f is 1. At later times, if V and W don't commute, then the real part of f is less than 1. So one can see that this measures the failure of initially commuting operators to commute at later times. And this quantity is of interest because it's been proposed to quantify the spread or scrambling of quantum information across the system's degree of freedom. Chris talked about this yesterday. Generally, this is a hard object to measure, but people are coming up with more and more clever ways. And so what Chris talked about yesterday is a very clever way to measure scrambling. And that was a 6-qubit system, if I remember that. But if we can time reverse the dynamics, then it turns out it's going to be possible to measure this quantity. And for our and in quantum simulators, it's frequently possible to time reverse the dynamics. And for us, where we only interact with one mode, that's easy because we can jump the spin-dependent, the frequency of our spin-dependent force from being slightly greater than the center mass mode to the same distance below. which just changes the sign of J. So we use this ability to time reverse the dynamics to do a many-body echo. We follow a protocol which was invented in NMR, known as multiple quantum coherence protocol. Tobias?
Don't you have to reverse your magnetic field then too? So something with the phase of the RF?
Don't we have to reverse the magnet? Not in this pure spin interaction.
It's pure.
So we're maybe I didn't emphasize that in this. When we apply this Ising interaction, we apply it for the length of time so that we close the loop, and there's no transverse field being applied here. So this is getting into the details. So we start with this protocol gives us is what we use to measure an atom-time order correlator. But the protocol, let me describe the protocol. We apply the Ising interaction, so that generates a squeeze state. We then invert the Ising interaction. If we don't do anything in between, we should get back the state we started with. That's this fully polarized state, given by the blue disk. In general, we're going to do a rotation about the x-axis, gives us the green state, and then when we invert, we get something different. It's the green distribution. At the end, we have to do a measurement, and we did two different measurements. What the theorists like us to do is the many-body overlap of this final state with this initial fully polarized state, and that's something we can do even in global fluorescence for about 100 spins. I'm going to show you measurements of the average magnetization along the x-axis. So the protocol calls for not just doing this measurement, but measuring it as a function of the rotation angle, and then calculating the Fourier coefficients of this measurement with respect to the rotation angle. And why this quantity is of interest is it tells us something about the state that we're creating right at this time. I'm going to leave out details, but one can show that if one has a non-zero nth order Fourier coefficient, then that means that this state psi has correlations, has spin correlations of at least order n. And briefly, one can show that this measurement is the same as an OTOC by grouping these operators. So here we write out the operator definition of the measurement we're making. And if we group these operators as indicated here, we can see that this is a measurement of an OTOC. We're taking advantage of the fact that we're starting with an eigenstate of S sub x, which is the operator B. So we can insert an extra instance of B here. So let me show you some measurements. So we squeeze, we rotate, we unsqueeze. So this shows measurements of the average magnetization at the end of the sequence. This is done on a crystal of about 111 ions as a function of this rotation angle here in the center. If we don't do a rotation, we should get back 1, but we're getting back something less than 1, and that's because of experimental imperfections. The two that go into these theory calculations are spontaneous emission due to the off-resonant laser beams and also magnetic field fluctuations. When we're at a rotation which is different than 0, we see that the OTOC decays much more quickly. For these longest interaction times, we see the magnetization is changing signs, so this corresponds to these oversqueeze states. And now what we're interested in are the Fourier components of these different measurements with respect to the rotation angle phi. And so this shows the Fourier components for the data that was shown on the previous page, and then other times. So each vertical slice here corresponds to a Fourier spectrum at a given interaction time. You can see that we start out with what was a flat line, so just one Fourier component. We start getting some oscillations that gives us an m equals 2 and m equals 4. We can see up to m equals 8. As these higher order Fourier components build up, the lower ones decay away. We get good agreement with theory, and we also get good agreement, fairly good agreement with theory, which ignores deep decoherence. So this indicates that we are observing coherent quantum dynamics in this system. Couple points to make: that we're measuring the buildup of 8-body correlations, and we're doing that with the global fluorescence measurement, so it's kind of a nice trick of this system. I'm going to skip talking about this because time's getting a little short. So what we like to do in the future is, if we apply a transverse magnetic field, this gets to your question, Tobias, then we can't realize a pure spin model, but we realize this Dickey model, and we can time reverse the Dickey model. And so doing an OTOC measurement with the Dickey model should be interesting, because it's known that that the classical Dickey model exhibits chaos in certain parameter regimes. So we should be able to observe much more rapid chaos. And this is discussed in this article by Robert Louis Swan and postdoc on a rearray. So how much time?
5 minutes.
5 till 30, or?
5 till 35. Yeah.
Okay, so let me briefly describe how we hope to get stronger interactions, and that's to parametric drive the phonons. And so this idea can be illustrated if we think about a single spin, and it's most easily illustrated if we think of the spin-dependent force frequency being resonant with the center mass mode. So if we have a resonant spin-dependent drive, then we drive straight line paths in this phase space for the center mass mode. So spin up will go this way, spin down will go that way. We need to close the loop. We can do that by jumping the phase of our spin-dependent optical dipole force. And so this shows a protocol where we do 4 segments where we jump the phase by 90 degrees. Each segment has a length, has a displacement alpha, and so the geometric phase is going to scale as alpha squared. So we'd like to amplify this, but we don't want to increase our laser power, because spontaneous emission is going to increase if we do that. Can we do that? And the answer is yes, we can. And we can do that by using the squeezing operator. This is the motional squeezing operator. And the point to make is that this is straightforward to implement in ion traps just by modulating the trapping potential at twice the motional frequency. And so I point you to, this is a fairly recent work. This has been published now. This is from the NIST group, Sean Bird, where in a surface electrode trap was able to generate this G here of greater than 50 kilohertz. So in a few microseconds of squeezing, you can get squeezing parameters greater than 1. This C here greater than 1. So how can we use the squeezing to amplify a spin-dependent force? The easiest way to see that is to use this identity. If we squeeze with the right phase and then do the spin-dependent force and then unsqueeze, that's the same as doing a displacement which has been amplified by this factor, e to the r, or r is the squeezing parameter. So one can just amplify each segment by doing the appropriate squeeze, unsqueeze, and then another squeeze, unsqueeze with a different phase, and amplify each segment, which can amplify our geometric phase by this factor, e to the 2r. So this protocol was discussed in this paper. So, like any tool in the trapped ion toolbox, I'm proposing this to be another tool that we can add to that toolbox, but there are going to be trade-offs. It might make sense to implement this in some systems and not in others. I'll refer you to this paper by Wenchao Gi and Michael Foss-Feig. Brian, Joe, and I were kicking this idea in the lab. We were kicking around this idea in the lab a number of years ago. We could never really figure out how to implement it. And it was these two guys that taught us how to do that. This particular protocol is different than the stroboscopic protocol, which I just described. It applies the spin-dependent optical dipole force and the parametric amplification are applied simultaneously and continuously. So you actually do circles in this transformed phase space. And now the drives don't have to be resonant with the center mass frequency, they can be off resonant. And it discusses some of the trade-offs where this technique might be useful. I'll advertise, so we hope to implement this in the penny trap experiment sometime in the next number of months. I'll advertise that this has been implemented in the NIST surface electrode trap experiment. This is where the ions are trapped about 30 microns above the surface, and the spin-dependent forces from magnetic field gradients. And they've been able to see a speed up in an entangling gauge of about a factor of 2 to 3. So,
You have 2 minutes.
okay. So I'll just briefly summarize. Ions are known to be sensitive force detectors. There have been lots of papers. The basic scheme, typically in most of these papers, is one takes motion and maps it onto the spin and then measures the spin. Most of these demonstrations have been done with a single spin, but if we use an anion crystal, there are some advantages. In particular, a given force per ion is going to excite a single ion to the same, or a given force per ion is going to excite the center mass motion of an anion crystal to the same amplitude as a single ion crystal. But now we can map this onto the n+1 levels of the Dickey manifold and read this out with better signal to noise. So we are running out of time here. I just want to say that using this protocol in an experiment where we put a tickle, off-resonant tickle on the end cap, and we move the center of the trap up and down far from resonance of the center of mass mode, we can demonstrate that we can measure a 200 picometer amplitude in a single measurement. This was done where the phase of the spin-dependent force was not stabilized. Recently, we've been able to stabilize that phase, and now in a single measurement, we can measure a 50 picometer amplitude. And given the rep rate of the experiment, that's around 10 picometers in 1 second. So the sensitivity looks really good. What we'd like to do this is on resonance. Now we have to worry about thermal and zero-point fluctuations. There are protocols with which they can be canceled out. But one thing we're running into is that there are fluctuations of our center of mass mode currently at the 50 hertz level. That's going to limit the sensitivity we get on resonance. So let me just close by saying we need to increase the complexity of our system, and one thing we're going to try to do here in the next year is implement local spin flips rather than just global spin flips, improve our single ion readout. Hopefully we'll get some gain with this parametric driving. Interesting question is, can we extend this weak force sensing to 3D crystals where we'd be even more sensitive to electric fields? And close with this picture of the people who have done the work. So thank you.
We have some time for questions.
So when you apply this spin squeezing Hamiltonian, of course when you go this full time you get this Schrödinger-Cat state. One can visualize as two blobs on the block sphere. But then when you go root n shorter, you find these kitten states where you have multiple copies of
Okay.
Have you seen any evidence of non-Gaussian wiggles at these magic times?
So I would say no, because we're probably just starting to get into that regime. So I said 10% of the cat time. So if we have 100 ions and you're one of a root n state, we would say that they're probably just starting to form where there's a large number of blobs going around. And no, we haven't seen that. If we can reduce our decoherence through the spontaneous emission, say by the parametric amplification, with ground state cooling, we can open up the angle between our spin-dependent force beams. That gives us a stronger spin-dependent force for a given amount of spontaneous emission. So if we can make those improvements, I say we have a chance of seeing something.
John, your transparency said that your force detection can be used for axion search.
Yeah, so that's, so I guess the statement is, once you're in this nanovolt per meter sensitivity, that sensitivity looks good enough to place new limits on axion couplings to normal matter or hidden photon couplings. What we aren't taking into account here that needs to be analyzed carefully, this is just the raw sensitivity, the shielding effects due to trapped electrode and the Compton wavelengths. So we would measure axions which would have a time dependence, which would be resonant with their center mass mode frequency.
Dark matter wind that goes through the
Yeah,
apparatus.
so this corresponds to dark matter where the mass is 10 to the minus 8 to 10 to the minus 10 eV, something like that. And so it's a classical field which is oscillating. This is what I've been told, I can't explain it. And so it's this classical background field. That classical background field isn't going to just interact with our crystal, which is sitting in the center of the trap, but it's going to interact with the electrons in the walls of the trapped electrodes. I've been told that these very long Compton wavelengths, so for instance, if one has an experiment sitting on the ground, which we would have, there are shielding effects where the wavelength is long compared to the distance from the Earth, which acts as the ground, and where your experiment is. So, you know, the sensitivity gets us in a regime which is interesting. Before we make a claim that we can really search for axions, we would have to think carefully about these shielding effects and get someone who knows more than I do about this.
So along the same lines of that question, how does the larger number of ions help you with sensitivity? So that seems intuitive that it would, but having a larger number of modes doesn't seem like obviously a good thing. So how does that not from one to the other?
Yeah, so it let me just go back. It helps in the sense, so if we're searching for a weak force where that force is a force per ion versus the same force over the whole crystal, which is a given force per ion will excite this Ni crystal to the same amplitude as this. So that's how it's going to help, because now we can read it out with better signal to noise. The 0-point fluctuations of the center mass mode are smaller. Now you bring out, maybe if you have a 500,000 ion crystal, you have a lot of modes, and so yes, you would have to find a rotation frequency where that center mass mode would be well separated from all the internal modes. One nice thing about having a trap where you have a good quadratic trapping potential, as you know, in principle, the center mass mode doesn't couple to the other modes. I can say we've done one ring down experiment where in crystals like this, we excite it up to 50 nanometers and then watch it ring down, and the ring down time is longer than 100 milliseconds. So the energy sharing is slower and is less of a problem than the frequency fluctuations, which we're currently running into, which is going to limit our sensitivity.
Is the basic idea though that you get a single quantum difference between population of one mode versus another for a smaller amplitude in the anion crystal? Like the same amplitude gets you one mode versus another, or a smaller amplitude rather gets you one mode versus another?
I think of it more as we're going to get a certain spin precession angle, and we can read that out because the projection noise on our block vector is root end better. But you might be saying the same thing, and I'm just not figuring it out.
Well, I think we have to go forward. Let's thank John again very much.